Aloha BIOCHEM. In this video, we discuss acid-base reactions. So we're moving along in Chapter 9. This time we cover sections 9.2 on acid-base reactions and also touch on 9.3, acid and base strength. Let's recall at the end of the previous video, we took a look at several examples of acids. These are the chemicals that release protons in solution and also donate protons when they react. And we also looked at some examples of bases which release hydroxides in solution, and they also accept protons when they react. So in this video, we're looking at acid-base neutralization reactions, which are also called proton transfer reactions. Our first example involves the reaction between hydrochloric acid and ammonia, which is a base. You can see from the chemical formulas in the equation that a proton has been transferred, and that HCl is donating the proton, and after donating it, it turns into Cl-, so this is called the conjugate base of HCl, and ammonia is accepting that proton from the acid, and after accepting it, it turns into NH4+, and this is called the conjugate acid of that base. So the proton has been transferred from the acid over to the base, and those are the products. There are always two conjugate pairs in an acid-base reaction. So the ammonia and the NH4+ are one pair. This is the basic form, and this is the acid form. And then the HCl and the Cl- are the other pair. The HCl is the acid form, and the Cl- is the base form. Technically, on the reactant side, they're called the acid and the base, and on the product side, the conjugate acid and the conjugate base. But I like to think of them as pairs. So you got one pair. This is the base form, that's the acid form, and then you got the other pair. This is the acid form, and that's the base form. Always two conjugate pairs in an acid-base reaction. Now we can get a little better view of what's going on here by drawing the structures of the molecules and particles involved. For the reactants, we have hydrochloric acid and ammonia in solution. The hydrochloric acid is dissolved as H+ and Cl-. And of course, the H+ are always associated with the nearby water molecule. So an H+ in solution is a hydronium ion in solution. What happens is the base, the lone pair on the ammonia, grabs the proton from the acid, and in doing so, it turns into NH4+ called ammonium, and you can see the lone pair is now used to bond to the proton. And the electrons here go back to the water molecule, so you get your water molecule at the end, and of course chloride still left at the end. This reaction produces ammonium chloride, and ammonium chloride is a mucoactive agent, and so this substance right here, NH4Cl, is found as the active ingredient in some medicines that help thin down your mucus and clear out your system. Our next example shows us that even dissolving acids or bases in water can be viewed as acid-base reactions. So in this example, we'll look at dissolving a strong acid in water. And for the strong acid, we'll take hydrochloric acid again. So here, when you dissolve hydrochloric acid in water, what happens is it donates protons, and when you have protons in solution, they quickly get associated with water molecules. So that right there is an acid-base process. So the water molecule acts as a base because it associates with the proton from the acid. And so, when you dissolve an acid in water, think of this as right after you dissolve it in water and right before the proton gets associated with the water molecule. Okay, so here's your acid, there's your water molecule, this is right at the beginning, and then the proton latches onto the water, and that forms hydronium, and then you have the chloride left over. So again, the HCl donates the proton. This is the acid, and that's the conjugate base. And then the water accepts the proton. So this is the base, and that's its conjugate acid. Always two conjugate pairs in an acid-base process. Now, if you want to picture what a solution of hydrochloric acid looks like, well, here it is. 100% of the HCl molecules release protons in solution. They are all in the form of H3O pluses, and so you have your chlorides in there as well. So HCl is a strong acid because all of the molecules do this. Okay, the reaction does not go back in the opposite direction. Sometimes chemical reactions do not proceed all the way to completion, but strong acids release all of their protons in solution. The conjugate base chloride has no tendency to reclaim that proton, if you will. Okay, it's a very, very weak conjugate base. Hydrochloric acid, there's a nice picture of it in your textbook here. It's the main acid that's found inside the stomach in your gastric juice. So here's your stomach, and it's a very dangerous acid as well, and so your stomach has a thick lining of mucus which protects it from the hydrochloric acid that's inside the stomach. So the hydrochloric acid, of course, is 100% dissociated or 100% ionized into the chloride minuses and the dissolved protons. And that's what helps dissolve your food. So here's, another picture of hydrochloric acid in solution. It looks just like water. You can't tell the difference, okay? But, it's 100% dissociated. Strong acids completely dissociate in water. In example 3, we look at dissolving a weak acid in water. And this is also an acid-base process. But weak acids are a little bit different than strong acids because it's a partial ionization. Not all of the molecules of weak acid ionize. So hydrofluoric acid is a weak acid, and when it dissolves in water, it does release protons in solution, but only some of the molecules do this. So the ones that do, the HF, after releasing the proton, turns into F minus, and so F minus is the conjugate base of the acid HF, and the waters accept any protons that are donated to turn into H3O plus, and this is the conjugate acid of that base. Always two conjugate pairs in an acid-base reaction. Notice though the two-way arrow here, the equilibrium arrow is used to acknowledge the fact that this reaction does not go all the way to completion. In fact, if you want to visualize what a solution of HF looks like, it looks kind of like this. A couple of the molecules, a few of them have dissociated into protons and fluoride minuses, but the vast majority of the molecules are dissolved as whole molecules. In fact, for hydrofluoric acid, about 1 in 12 molecules actually ionize. So this is a weak acid. It's not really weak. There are other acids that are even weaker, you know, some acids, maybe 1 out of every 100 molecules ionized, or maybe 1 out of every 1,000. So some of them are really weak. But this is still considered a weak acid because not every molecule ionizes. And if you want to, you could say because of that, these conjugate base anions, you know, kind of have an attraction to the protons that they don't want to separate, in other words. There's more of an attraction between F minus and protons. So, you know, this is a little bit different situation than that HCl. When HCl dissolves, the chlorides are very comfortable in solution. They have no tendency to grab those protons and reform the molecules. Okay, they're happy in solution as is. But the F minus, you know, it kind of likes protons a little more. So you see a lot of HF molecules in there, and that's because the F minuses are grabbing those protons. So the conjugate bases of weak acids are a little bit more basic than the conjugate bases of strong acids. Now, here's a little comparison between several acids. So hydrochloric acid, this is a strong acid, and strong acids completely dissociate into solution. So if you have a solution of hydrochloric acid, 100% of the molecules ionize, and so you will find no molecules of HCl in here. They've all ionized. Okay, and so the chlorides have no tendency to grab those protons. They're happy being separated from one another. Now, HF, hydrofluoric acid, is a weak acid, and we just took a look at this one. It's a weak acid, and about 1 out of every 12 molecules ionizes. So you'll have a few protons in solution and a few fluorides, but most of the HF is in the form of undissociated molecules. So we say that the F minus kind of has a tendency to grab onto protons again. Okay, so the conjugate base this time is kind of basic. But there are even weaker acids than HF, and acetic acid, which has the formula CH3COOH, is even weaker. 1 out of every 75 molecules of acetic acid will ionize typically in solution. And so you might have a proton here and there, and the acetate anion, but the vast majority of acetic acid in solution is as undissociated molecules. And so we say that the acetate anion, would much rather have a proton. It's more basic, than the F minus. The F minus, is kind of basic, but the acetate anion is more basic. So as you get to weaker and weaker acids, the anions, those conjugate base anions, get to be more and more basic. Now, the strength of an acid can be quantified by what's called the acid dissociation constant. These are the Ka's that I have up here. And the smaller the Ka, the weaker the acid. So acetic acid has a Ka of 1.8 times 10 to the minus fifth. That's 0.000018. That's pretty small. Hydrofluoric acid has a little bit larger Ka. It's of the order of 10 to the minus fourth, 3.5 times 10 to the minus 4, so that's 0.00035. And then hydrochloric acid is a strong acid. And strong acids all have infinite Ka's. Their Ka's are in infinity. Okay, so there's a nice picture in your textbook that compares strong and weak acids. So I'll point that out to you. This is figure 9.4. So here you have solutions of hydrochloric and acetic acid. So that's hydrochloric acid. It's a strong acid. 100% of the molecules ionize, and acetic acid, which is pretty weak. The Ka is 10 to the minus fifth. Okay, so, and if you look at the solutions, they look just like water, but zoom in on the solutions, you'll see hydrochloric acid. All of it is ionized. So you will find no HCl molecules in here. They've all split apart. But acetic acid, on the other hand, most of them are molecules, but every once in a while you'll find, an H3O plus and the corresponding anion. And so that's the kind of picture that you should have in your mind when you're thinking of strong acids versus weak acids. So all of them have ionized, or some of them have ionized. Now, like we mentioned before, there is a range of acid strength, okay? And table 9.2 describes, it has a big list of acids, and it goes from strongest down to weakest. And so up here you have these 5 acids. They're all strong acids, and strong acids are kind of on the same playing field. All of them 100% ionize into solution. And so here's some strong acids. Here they are, the 5 strong acids: hydroiodic, hydrobromic, hydrochloric, sulfuric, and nitric. Usually textbooks have 6 strong acids or 7, but the other one that I can think of, perchloric, isn't on this list, and there is another strong acid or 2 that are out there, but this is a pretty comprehensive list right here. So here are the acids, and after they release protons in solution, those are the conjugate bases. Okay, those anions are the conjugate bases. Now, as you go down this list of acids and you get into the weak acid region, phosphoric acid is at the top of the list. Phosphoric acid, H3PO4, this is a triprotic acid. It can release 3 protons in solution, but it's a weak acid. So not 100% of these molecules ionize or release their protons. But the ones that do, after they do it, this is the conjugate base. As you go further down this list, you get to weaker and weaker acids, and eventually you start to approach the strength of water itself. Water can act as an acid, and even a tiny fraction of water molecules ionize into protons. We'll talk about that in a future video, but hydrocyanic acid is a really, really weak acid. Now we saw that as you get to weaker and weaker acids, the conjugate base anions get stronger and stronger. So, as the acids get weaker, their anions don't like to give up their protons. That's how you think of it. As you get to weaker acids, the acid molecules don't like to dissociate, and that's because those anions like to latch onto those protons. They don't let them dissociate. Okay, so the conjugate bases get stronger and stronger as you go down this list. All right. Now there's, before we take a look at several examples, this is the last thing we'll do, is look at several examples of acid-base reactions and predicting which direction they go. I want to at least mention bases. All right, when you have bases, maybe I'll go back to the previous previous lectures, last slide here, the last part. The ones that are highlighted right here with the stars, these are the strong bases. Strong bases are metal hydroxides that dissolve in water, soluble metal hydroxides, okay? And they're strong bases because 100% of these molecules ionize into, the hydroxide anion, okay? So for every one of these, you get a hydroxide anion. Now the weak bases, on the other hand, you don't see hydroxide in the formula, but when you dissolve it in solution, you do end up with hydroxides. So they still cause ionization in water, and you get hydroxides, but it's not 100% ionization. So let's see how this works. So when you have, say, let me blow this up over here. When you have, say, a strong base like sodium hydroxide, when this dissolves in water, 100% of the formula units, this is not a molecular compound, this is an ionic compound, so 100% of the formula units split apart into the metal cations and the hydroxide anions, and so that single arrow represents a one-way process. Now weak bases also give you hydroxides in water, but they do so a little bit differently. The way it works is it basically takes a proton from water, and that leaves a hydroxide. So after water releases gives up its proton to this weak base, you get the hydroxide. Now, not all of the weak base molecules do this, just a small fraction of them do this. So for every one of these, for every 100 weak base molecules, you might just get 1 or 2 hydroxides. But if it's a strong base, for every 100 of these, you'll get 100 of those. Okay? So again, weak and strong. Okay, strong, 100% ionization, weak, small fraction of them ionize. And if you want to compare, say, a solution of sodium hydroxide versus a solution of ammonia, well, the sodium hydroxide, all you'll see in the water are the sodium ions and the hydroxide anions. But if you have ammonia in water, you'll have some of the ammonia ionized into NH4 plus and OH minus, but the vast majority of the ammonia is simply as dissolved NH3 molecules. Maybe 1 out of every 100 of the NH3 molecules will ionize. Move this back out of the way. Okay, the last thing that we'll do in this video is we will compare or predict, really, the direction of an acid-base reaction. So what we're going to do is take a look at 5 different chemical reactions that occur between acids and bases, but the strength of the acids and bases ranges. So some of them will be strong acids and some of them will be weak acids. So we'll start with strong acids reacting with strong bases, and then we'll get to weaker and weaker systems. So first, let's take the strong acid, hydrochloric acid, and the strong base, sodium hydroxide. Now, this reaction is a one-way process because when you think of a strong acid, you should think that this chemical has to donate its protons. Strong acids donate 100% of their protons. So this guy must give up its proton, and strong bases must accept protons. So this reaction must proceed 100% to form the salt in the water. Now let's take a strong acid with a weak base. This is the conjugate base of the acetic acid. You remember, acetic acid is a weak acid, and so after some of its molecules release protons, but that conjugate base, it has an attraction to protons. After all, only 1 out of every 100 or so molecules dissociate. So it does attract protons. So when you have a strong acid that must give up its proton, reacting with CH3COO-, which kind of kind of wants a proton, but it allows some protons to stay in solution, but it kind of wants a proton. Then this reaction, pretty much proceeds. Okay? It pretty much proceeds to form the products. After receiving the proton, this is the conjugate acid of that base. And after giving up the proton, this is the conjugate base of that acid. If you react a strong acid with a very weak base, like F minus, okay, so in the form of sodium fluoride, F minus is the conjugate base of HF. So the F minus even has less of an attraction to protons as the acetate, okay? It allows more protons to be dissolved in solution, okay? And so this guy doesn't really want protons as much as that guy, right? When you remember the picture, this one allows less protons in solution. It wants protons more than that one. This one allows more protons in solution, so it doesn't really want them as much as that one does. And so when it's playing the role of a base, it doesn't really want the protons as much. And so this reaction doesn't really proceed as much as the last one. And so there is a tendency for it to react in the backwards direction. So the reaction does not go to completion as much as this one did, or as definitely as much as that one did. So as the base gets to be weaker and weaker and weaker, it's like it doesn't really want the protons that the acid is trying to give it. And so the reaction doesn't proceed as much. Now, instead of strong acids, let's take a look at a couple of weak systems. So suppose we take a look at hydrofluoric acid, which is a weak acid. Remember, hydrofluoric acid, 1 in 12 molecules dissociates. So it likes to give up protons, but it's not a strong acid. It's a weak acid, moderately, not really weak, but, weak. So it likes to give up protons. And let's combine the HF, which likes to give up protons, with the acetate, CH3COO- in the form of sodium acetate. Okay, and acetate, is a weak conjugate base. It's not as weak as F minus. It's a weak one, so it likes to have protons. It allows some protons in solution, but not that many. And so this guy, which likes to give up protons, reacts with that guy, which likes to accept protons. And so the reaction kind of proceeds. Okay, maybe it proceeds a little bit more than it goes in the backwards direction. So, it proceeds to the products somewhat. For the last example, let's take a look at CH3COOH, which is the weakest of the acids of the three that we've considered. And let's react to this with NaF. So this guy, CH3COOH, is a very weak acid. It sort of gives up protons if it has to. Okay, and the F minus is a very weak base. It sort of accepts protons. It's the weakest of the bases. This is the weakest of the acids that we've considered so far. And so when you put them together, it's like, okay, we'll do a proton transfer reaction if we have to, but most of us aren't going to do it, So some of it will react. The proton will be transferred a little bit, but most of it will not. Anyway, I hope you see that as the acid gets weaker and weaker and weaker, its ability to transfer the proton diminishes. And as the base gets stronger, its ability, or as the base gets weaker, its ability to accept the proton diminishes as well. So, hopefully this helps you understand, something about the direction that acid and base reactions go. And you can maybe use let's take one more look at this diagram. You can use this diagram to predict whether acid and base reactions will proceed. So this figure lists acids. Here's the strongest acids, here's the weakest acids. So table 9.3. You know what? Let's go back to table 9.2. This is a little better because this has the anions. So table 9.2, these are the strongest acids and these are the weaker acids. Now their corresponding conjugate bases, these are the weakest. The stronger the acid, the weaker its conjugate base anion. Okay, because if the acid has to give up a proton, its conjugate base doesn't really want it back. Okay, so as the strength of the acid decreases, the strength of its conjugate base increases. These acids don't really want to give up their protons because their conjugate bases really want them. And so if you want a reaction to proceed, select an acid that really wants to give up a proton with a base that really wants to accept it. So take somebody up here in the acid part and take somebody down there in the base part. Okay, if you want a reaction that doesn't really happen, doesn't proceed, take an acid that doesn't really want to give up its proton, a weak acid, and match that up with a conjugate base that doesn't really want to accept the proton. So take a pair from this part right here. Okay, so hydroiodic acid reacting with hydroxide or cyanide, that reaction would, go all the way to products probably. But if you mix, say, hydrofluoric acid with the the bicarbonate anion, okay, that might have a tendency to go. But if you want a reaction that doesn't really go, maybe select the fluoride ion with ammonium. That won't really go to products that much. And if you want a reaction that hardly goes to products at all, select somebody up here like the bromide minus and mix that with hydrocyanic acid. Okay, that won't really proceed hardly at all to products. So that's it for this video. In the next one, we will discuss a little more on acid strength, but we'll talk about it in a quantitative way through their acid dissociation constants, Kas. So stay tuned for that. Aloha.